Development. I'm going to talk about glass in space, and perhaps in addition to glass, some of the liquids that are used to create glasses. Glass is an important material, and I'm going to just review the sort of past, present, and future, because what we're really interested in talking about here is the future of glass and how glass technology can be advanced through microgravity research. Natural glasses are abundant in space, on planets, and in cosmic dust. They've been around for hundreds of millions of years. That inset image is a piece of obsidian, which is a silicate glass that's widely present along with olivine throughout the universe. The earliest man-made glasses date back several thousand years. The image there is actually the Lycurgus cup. It's a piece of Roman glass, so it's not quite that old, but it indicates the level of detail in glass working that was achieved even many years ago. Moving up to probably the sort of 50 to 100 year range, the 60s through the 2020, functional glasses have really underpinned technological revolutions. Lasers and photonics and optical communications, displays and electronic substrates, and medical applications. This is actually a bone substrate. Glasses are also used in drug delivery systems. And then in the mid-1980s, the first glass processing in space was done. The image actually shows the space station. Those first experiments were done on the shuttle. But glasses were made in space and then brought back to Earth for analysis and characterization. And then currently, some of the instruments on space station are being used to benchmark the properties of glass-forming liquids. And in fact, one of MDI's experiments uses this system, the JAXA electrostatic levitation furnace, to measure thermophysical properties, which is an area that we're very interested in. So let's take some steps into the future. Let's think about areas where glass is going to contribute and areas where there are still questions relating to glasses and that can be answered perhaps using microgravity. Most glasses are based on what are called strong liquids. Basically, glass processing is about controlling viscosity, controlling the flow of a liquid, because in many respects a glass is similar to a liquid in terms of its structure. It has short-range atomic ordering, but it doesn't have long-range order like a crystal would. So strong liquids are liquids that have a more or less linear increase with viscosity as they're cooled. In fact, if you plot the logarithm of viscosity versus inverse temperature, it's more or less a straight line for things like silica that make up the vast majority of commercial glasses. There's a whole class of liquids. Nearly all oxide liquids and metals and other materials are called fragile liquids, and they don't have this property of viscosity. The viscosity doesn't change much when you start cooling the liquid down. And then if it forms a glass, it suddenly increases. So there's this huge number of glasses that haven't really been explored. And what is the potential for those? Just look at what glass has achieved over the last 100 years and imagine what could be done if you had a whole family of glasses that you never had before, that you could draw on to solve technological problems. Now, low gravity suppresses buoyancy. One of the things that occurs in glass often is bubbles, and bubbles can be good or bad depending on what you're trying to achieve with the material. Sometimes you have a glass that has immiscible phases, think oil and water, and the two phases phase separate, and controlling that phase separation can be important. Imagine if you could create photonic crystals by adjusting the way that phase changed and moved around within the melt as you were making a glass. So you could create a 3D structure in the glass by an array of the second phase. Also, heat and mass transport differently in microgravity because of the lack of buoyancy-driven convection, and that affects the way you can process materials and opens up new opportunities. So what kinds of glass products can be made by exploiting these types of effects? A very important area commercially and in research as well is using data-based models to optimize energy and materials use. This is increasingly important in developing functional glasses. So what role does microgravity play in gathering benchmark data? It's already being used for thermophysical property measurements. Those capabilities could be expanded considerably and open up new frontiers for measurements of properties and benchmarking materials. And that's important. Understanding the material is really at the heart of improving its properties. There are a number of emerging processes. Some of these are becoming somewhat mature now, and some of them are in their very early stages. Additive manufacturing, where materials extruded usually as a melt, although there are other techniques, and then built up. Freeze casting, ion exchange, and various laser techniques. How can these be exploited to expand the performance of glass products and add new types of materials? Space exploration often can depend on use of local resources. There's a lot of materials out there. There's a lot of glass, basically. Lots of things like olivine and obsidian floating around out there that could be used for building materials or actually refined to produce high quality glasses for optical applications to service missions. So what role can glass play in local resource utilization? It's already there, so it's relatively easy to harvest it and take advantage of that. Some materials are in short supply, even on the ground and certainly in space. So how could a premium glass be recycled and reused, especially in space exploration, but even for ground-based applications if it's a material of high value or rare properties? So this is where I bring out the crystal ball. I'm going to try to make some predictions. Unfortunately, I can't see the future exactly, but I can make some projections based on where we've been in the past and where we think we're going, and also optimism of the creativity and contributions that researchers are going to make in this field to bring new materials to fruition and develop new processes. I'm confident that new glasses are going to continue to underpin major technological advances, just as they have been for the last 50 plus years. Microgravity and space-based processing are challenging, but they do present interesting opportunities for processing and characterizing glass and new kinds of glass-forming liquids, and this is important. Bases in space will be built using local glasses. The better we understand those glasses and their behavior and their processability, the more likely we are to flourish in that environment. So that's important to NASA's direct mission, as well as being good fundamental science. Data and models increasingly drive innovation in glass technology and expanding its applications. So getting data, benchmarking and reference data are going to be important. Ongoing, and this is still something that NASA's already working on, and it's an area that needs to be built on and expanded, in my view, perhaps with ground-based capabilities as well to feed into that. So I look forward to traveling with you into the future on this enjoyable and exciting journey. So thank you very much for listening. Bye.